Hello viewers, welcome back. So in the previous video you had seen how AES works and what are its initial transformation steps. So we saw how AES takes the plain text of 128 bits and it undergoes few operations. The very first operation that we saw was key transformation, where we converted a 4-word key into a 44-word key so that it could be used for the 10 rounds that it would follow. Fine. Followed by that, we saw what exactly is initial transformation. So in this video, we'll complete AES and we'll see how AES actually works, what are the internal phases that take place in each round. So with that, without wasting much time, let's get started. So let's continue. So as you can see, we had seen this diagram in the previous lecture also. After the initial transformation happens, we have a 16 byte ka matrix, and this matrix is what we call as a state matrix. So as you can see, round number 1 consists of 4 transformations, and all the way over here, round number n, in this case we are using AES 128, so we will be having a 10 rounds AES. So the 10th round will be having only 3 transformations. So if I go ahead and show you this, as you can see, round number 1 till round number 9, that is from round number 1 till round number n-1, we will be having 4 transformations in each round. Whereas in the case of round number 10, we will be having only 3 transformations. So this is how AES standard works. And we are going to have a look at all these operations that happen inside each round. हर एक round के अंदर कौन से वो 4 operations होते हैं till n-1th round, that is 9th round, हम वो सारे operations one by one देखेंगे. So let's start with the very first transformation of round number 1, that is substitute bytes. Now what actually happens in S-box substitution is it consists of a standard S-box. This S-box is of size 16 by 16, as you can see. So we are having 16 rows and 16 columns. Now what actually happens over here is, for example, there is this matrix as you can see on your screens. This is nothing but the initial state matrix. उस state matrix का कोई भी एक value, if I consider, for example, over here we are having the value S11. So if I consider S11 as my current cell, so what happens is S11 is nothing but a 1 byte value, as this entire matrix is of 16 bytes, so S11 is of 1 byte. So what happens is 1 byte is nothing but 8 bits. So what we can do is we have to divide those 8 bits into, that is 4 bits ka 2 parts. So the first 4 bits will give you the row and the remaining 4 bits will give you the column. So in case if I'm having a input as 1011 1100. So what happens, I will take these 4 bits and I will consider that as the row. Similarly, the remaining 4 bits will be considered as column. So in my case 1011, it simply means 8421 के terms में अगर मैं लिखूँ, it will be 8 plus 2 plus 1, that is 8 plus 2, 10 plus 1, 11. So it will be 11th row. So just check what is 11. 11 in hexadecimal is, see over here, 10 stands for A, 11 stands for B, right? So I will be considering the B row, and similarly 1100, 8 and 4, 12. So I would be considering the C column from this particular table. So whatever is the intersection, that is B or C ka intersection, will give me a value 65. So I can easily say that 1011 1100, that is B and C, will give me an answer 65 in hex. So this is how substitute bytes, or the very first step, works in AES. It simply divides that entire 8 bit into 4 bits ke 2 groups. First 4 bits will give you the row, remaining 4 bits will give you the column. Or it could be in terms of hexadecimal also, as shown in this particular diagram. Let's consider 95, because all these values are hexadecimal values. So 95 ko we can convert in 2 parts as 9 and 5. 9 will give me the row, 5 will give me the column. So the entire process remains exactly the same. If it's in binary, it will be termed like this. If it's in hexadecimal, it will be considered like this. So this is how S-box substitution works. So let's go ahead and see the next phase that happens in round number 1. Next phase is what we call as shift rows. It is one of the simplest kind of an operation. As you can see on your screens, the shift row operation basically takes the entire matrix and it applies some kind of transformation. In the previous case, as we saw in the case of S-box, we just gave you an example कि एक particular cell का value कैसे हम substitute करेंगे. So that happens for the entire 16 bytes मैंने यहाँ पे एक ही एग्जांपल दिया है, वैसे 16 बाइट्स ऑपरेशन परफॉर्म होंगे, एस बाइट्स, सब्स्टिट्यूट बाइट्स, एंड वी विल गेट सम मैट्रिक्स. सो एज यू कैन सी, आफ्टर ईच राउंड we are going to get the matrix. So after substitution round takes place, substitute bytes take place, we'll get one more 16 bytes ka matrix, and that 16 byte goes into shift rows. So we are going to apply shift rows on the output of substitute bytes. Clear? So let's imagine that this is the output of substitute bytes. This is the matrix. So what we'll do is we'll take this entire matrix and apply some kind of transformation. That transformation is nothing but it is 0, 1, 2, 3. So it simply means, as you can see on the right hand side, the first row is not shifted by any value, whereas the second row, or in this case this particular row, is shifted by one position to the left cyclically. So this 6e, which was at the second position, now goes to the first position. Similarly, this ec, which was at the very first position, now goes to the last position, and so on. In the same fashion, the third row will be shifted by 2 positions. So 46 will come at the first place, and similarly C3 will go at the last place. And finally, the last row will be shifted by 3 positions. So as a result, A6 will take the pole position or the first position in the final matrix. So this is how the shift row transformation works. I hope you are clear with this. Fine. So let's go ahead with the third transformation, and that is the most crucial one out of all. That's what we call as the mixed column transformation. So once we get the output of shift rows, we'll have a 16 byte matrix, and that 16 byte matrix will be further undergoing an operation called as mixed column transformation. So let's see what it is and how it works. Mixed column transformation simply looks like a matrix multiplication. As you can see, this is one matrix given, a 4x4 matrix. Similarly, another 4x4 matrix. This second matrix is what we call as the state matrix. That is nothing but the output of the previous step, that is shift rows. So these 16 bytes will be undergoing an operation called as mixed matrix multiplication or mixed column transformation. So it is nothing but a matrix multiplication with a standard matrix which AES follows. So this standard matrix is 2, 3, 1, 1, and the pattern continues. If you see 2, 3, 1, 1, 1, 2, 3, 1, 1, 1, 2, 3, and again 3, 1, 1, 2. If I iterate it once again, it will again become 2, 3, 1, 1. So what exactly happens is it is being shifted to the right by 1 position. In the third row, it is moving by 2 positions. In the fourth row, it is moving by 3 positions, and so on. So this is a standard matrix which you have to memorize. This matrix is multiplied with your state matrix at that particular instant, and we will get some output. It's very simple, very similar to what we do in matrix multiplications. But is it that simple? No, because if you see over here, all the operations of additions, they are not simple additions, they are actually XOR operations. So if you want to find out S0J, or if you want to basically find out this, in ideal scenario what will happen is, जब matrix multiplication होता है, so this 2 will be multiplied by this value, plus this 3 will be multiplied by this value, then 1 will be multiplied by this value, and this 1 will be multiplied by this value, and all these values will be added up. But in this matrix multiplication, we are doing all the operations over Galois field 8. That is, any operation we are going to perform that will be restricted or limited to 2 raised to 8 values only. So what exactly happens over here is, instead of addition, we are applying XOR operations. So whatever be the output, it can never go beyond 2 raised to 8. So how to do this? It seems very simple, XOR operations perform karna hai, but it is not that easy. Let me break this down and let me show you how we can perform this kind of an operation. So in short, I am assuming that 2 into S0J is what we want to find out. But we can't multiply it simply. We have to multiply it over the Galois field 8. So for that purpose, we are going to make use of this particular table, as you can see on your screens. This table is what we call as, or these tables are what we call as an L table and E table. Now how to make use of it? Suppose I have taken an example. Suppose I want to multiply AF and 8 over the Galois field 2 raised to 8, right? So what we need to do is, we need to consider these values AF and 8, and we have to compare them with respect to some table that we call as an L table. So these are standard tables. You can simply Google search and you will find the values of these tables. So these values are not going to change. These are standard tables, right? So what we do is AF into 8. So we first of all try to find out L of AF. That is very simple. L of AF simply means find out A के रो में F कहाँ पे मिलता है. In simple words, find out where we get the intersection of A and F on the L table. So in simple words, A will give you the row and F will give you the column. So find out A row and F column, that is this particular value, we will get B7. It's quite similar to what we did in S-box substitution, right? So AF is nothing but B7. In the same way, the second value also, that is AF into 8, we were multiplying. So for the second value, 8 is nothing but 0, 8. So we'll search for the 0 row and the 8th column, and we will get some value as 4B. So now we know that AF and 08 over the Galois field is nothing but B7 and 4B. So now we have to multiply B7 and 4B. So for multiplication, it's very simple. Now what we need to do is we need to simply add them up. As I told you, this is not a simple multiplication. We are going to add them up and then we will refer the values in the final table called as E table. Okay. So now what we'll do is, as I have already mentioned, we simply add these numbers, that is B7 and 4B, and we will get some result as 102. Now what we need to do is, as 102 is greater than 255, because in hexadecimal notation, the maximum that we can get is 255. So what we'll do is, we'll convert that into a range of 255. So for simplicity, what we have shown over here is 102, in simple words, in decimal, it converges to 258. So we will subtract 255 from this and we will get the result. So in simple words, for example, any value which doesn't go beyond 255, then this step could be omitted. But over here, the value goes beyond 255. So we have to take a subtraction or complete a subtraction or take a mod basically to get the result within 255. Why we are doing this? Because this is over Galois field 8 or Galois field 8. So now what we need to do is, we need to subtract 255 from this value and we will get a result of 03 in hex. But is it my final answer? Not yet, because there is still a table called E table. So we have to convert the result back using the E table's reference. So it will be 03. So E of 03 is nothing but, check the 0th row and the third column, it is 0F. So in short, the multiplication of AF and 8 over the Galois field or Galois field 2 raised to 8 is OF or 0F, whatever it is, 0F. Clear? So this is how you got the output of one particular operation in mixed column transformation. So if we go back, this is how the mixed column transformation looks like, right? So for simplicity, I can assume that we got one of the values from these 16 operations. Okay, so एक value मिला है. In the same way, we have to perform all these operations. For record, these operations are not done manually. These are done by the algorithm over an implementation which could be a hardware implementation, or it could be running somewhere on any handheld device or any kind of a computer, right? So all these operations are done with the help of an algorithm running on a computer. So once we get the output, we know that now we have completed 3 phases of one round, and the final phase which is left is a very simple phase, that is add round keys. So add round keys is the simplest step which we already saw in the initial transformation step. We will simply be adding the round key that is provided by the key transformation phase for that round. So if you have not checked my previous video, kindly go back and check that, because you will come to know how we got the key for that particular round. So in round number 1, round key 1 will be used, that will be XORed with the output of mixed matrix multiplication, mixed column transformation, which we got just now, and we will get the result. So this is how one single round of AES works. If you see the diagram, let me summarize all these steps. If we start with a 16-byte ka matrix, that matrix initially goes through substitution round or substitution bytes as sub bytes, where it undergoes a simple substitution over a standard S box. Then we got the output. That particular output goes through a step called as shift rows, where we shift the rows by 1, 2 and 3 positions till we finally get a new value or new matrix, which we then move to the next phase, that is mixed column matrix multiplication. So after mixed column transformation phase, we will get some answer, we will get some result which we just now saw, to which the round key will be added, and we will get the output of round number 1. In the same fashion, all these operations will be performed repeatedly till round number n-1. So in our case, as we are performing AES 128, we know that AES 128 consists of 10 rounds. So out of those 10 rounds, 9 rounds will have 4 transformations, and the last round, that is the 10th round, will have only 3 transformations. In 3 transformations, whenever I say 3 transformations, I am simply skipping the mixed matrix or mixed column transformation. That is according to the standard. So these are the steps that are actually being performed in AES. So after all those operations, after the 10 rounds of operations, we'll get some output, and that output is nothing but your final ciphertext. So this is how AES works. I hope you got the understanding of how AES actually works and what are the internal steps that take place in advanced encryption standards. At the end of this, we get the final 128-bit ka ciphertext. So this is just done on one block. You can just imagine how many blocks of text, plain text will be there if we consider a large input, right? So it could be hundreds of blocks if we simply consider one paragraph of text. So it could be hundreds of blocks if we simply consider only one paragraph of text. So that is how AES works. So with that, we come to the conclusion of this topic called Advanced Encryption Standards. In the next video, we'll start with a topic called as IDEA, or International Data Encryption Standard. So stay tuned, subscribe to my channel and share it with your friends. Thank you so much.